Just want to welcome Marco again for the session. He's from CAEfatigue and a mixture of a bit of sales, but I think really good with the technical stuff as well. So thanks, Marco, for joining us and for hosting the session today.
Okay, thank you, Garrett. My sales aspect is more business development, but otherwise I would say I'm fully technical. And currently, right now, I'm essentially in between product management of CAEfatigue and business development for durability. And can you confirm we have multiple companies represented, right? It's not just one company.
Yes.
Okay, so yeah, please.
No, it's at least 3 companies, one university, and then 2 companies at the moment.
And the industries are varying?
So the one is from armored vehicles, another one is power generation and maintenance repair for the power generation, and then, as I say, one of the universities.
Excellent. So it's good for me to know, so I can keep a bit of a, let's say, broad angle and scope, right? And so that would be a bit for everybody. And I'll try to give you, my purpose today is to kind of, some of you might be already, let's say, familiar with the CAEfatigue. So I want to impart, rekindle with those that already have a bit of background, but also I'm going to assume that some of you might not have any knowledge at all about the product. So I'm going to give you a quick, brief overview. Let's, it's a closed circle, so let's please interact and let's, feel free to stop me. Let's not wait until the QA. We could also have a QA, but let's try to keep this as interactive as possible, and you can, satisfy any curiosity you might have on the fly. And yes, let's can I start then?
Yes, you're more than welcome, Marco.
Okay, thank you very much for organizing this, Garrett. And the idea is to cover CAEfatigue as well, a bit of Romax design. As I'll show very briefly, we combine the 2 things because they are part of the same architecture. And let me just give you, the familiar overview when it comes to Hexagon design and engineering, where we have a number of tools and capabilities. And within this range of capabilities from CFD to multi-body dynamics to finite element and materials and so on and so forth. Within this environment, we also have a dedicated vertical around fatigue. Evidently, the beautiful things about this portfolio is that we can maintain very, very high level interaction and let's say digital thread between the tools. So obviously, when it comes to fatigue, you need to have stresses. So primarily, we could say Marc and Nastran within the Hexagon D&E portfolio, but we also obviously accept external additional solution from third party like Abacus, Ansys, Hypermesh, NX, Nastran, and so on. So it is a fatigue capability that is solver agnostic. A strong connection would be also with multi-body dynamics tools, because that's where we get the loads from. In fact, we have workflows that are completely direct. Let's say don't need to go through the FE codes, and you can do interesting stuff directly through Adams and Romax. We also can obviously leverage on other additional workflows, where it's advanced manufacturing, where it's advanced material description for composites, and also workflow for vibroacoustics. It might involve even CFD and Nastran. So really, absolutely, let's say the scope is quite wide, and the CAEfatigue, it's I still call it the new kid on the block when it comes to fatigue analysis, because most of the tools that are there, more familiar, more famous than CAEfatigue, have been there for maybe 30 or so years. CAEfatigue has been around for, let's say, total of from conceptual inception to where we are today, maybe 8, 7 years. But reality, it's gained a lot of traction and became very visible. Initially with our frequency domain prowess, because this is coming from a lot of, let's say, services engagement, especially around the reputation and the work of Dr. Neil Bishop, that was the founder for CAEfatigue, that was then acquired by Hexagon. And then it was complemented with time domain capabilities. Because of the very, very specific nature of the tool, where we try to address needs, workflow, processes, we have added to this tool all the things that are needed to satisfy these processes. So it's not really created with a narrow mind, a narrow band mind. Okay, this is a fatigue tool. No, this is really addressing a number of needs, and this includes, for example, loads management, test design capabilities, and ultimately also robust design. And we are not stopping there. We are continuously, let's say, adding bits and pieces that make this a unique platform around fatigue and durability, context, and processes. So I'm going to skip some of the, let's say, the marketing stuff, but I just want to make you aware that because we are so recent on the map, we could take let's say, the satisfaction. We could have the satisfaction to create an architecture that was as modern as possible. So the integration with other tools, the digital handshake, but also the ease of use, the speed, the quality, and robustness. All these things have been tackled, from the onset. So all these things could be word. As I said, I just went really quickly on that slide because I just want to give you that the proof is in the pudding. So when you look at the architecture, the way we work with CAEfatigue, and by the way, this is also being already being copied by some of our competitors. But we have a workflow template operated. You could say that some others have done that before, but the way our templating, our architecture works is absolutely unmatched in terms of ease of use, speed. And as I mentioned, is so you would be essentially getting into frequency domain, time domain, robust design, or load management. So whatever you're doing, everything will be absolutely familiar right from the beginning. And you really need very little coaching, or not at all. And there are a lot of, let's say, pre-demonstrated processes and videos and examples to leverage upon. Because the architecture is very flexible. We call it visual random and vibration response when it comes to also the frequency domain, because we really give unique insight. And yes, there is a first question. Please go ahead, David.
Sorry, I might have missed something. One of the key things I wanted to ask is, all right, so do you have a capability, maybe you'll discuss it later, to do verification and validation? So to be able to bring in results, actual test results, compare and draw a comparison?
Up to a point, meaning that we have tools. For example, we have tools for adjustment factors based on targets, and robust design is one of those. We are, let's say, in the process of looking at what you are describing. Could be maybe sometimes it's referred to as model adjustment. But also in the general areas of scope of correlation, this is something that we are moving towards with model assurance criteria and things like that. But this is, let's say, still to some regard roadmap item. So we do some stuff, and I'll show some of the things that we can do, and maybe that might resonate or not yet. And maybe at the end you can comment further. Okay.
Thank you.
Okay, so with the first part of the architecture, let me just clearly, at least to give you a bit of understanding of the architecture. We have different modules. We operate in the time domain, which includes also the robust design tool right now. We might change that in the future. We have a random capability that addresses random response in a very advanced manner. And this might not necessarily require also fatigue analysis, because if random is all you want to do, we have essentially random response. Is superior to both Nastran random, for example, and also pattern random, which is another familiar tool for people that are familiar with the Hexagon tools. Then we can do vibration fatigue. And in the vibration fatigue domains, we normally refer to stochastic processes, but also sometimes you have sign sweep analysis, and maybe you want to combine deterministic sign sweep with random processes, or maybe you add random on random. So we have collected a number of capabilities that are more advanced, including some of these what we call surrogate loading, which is again in the same area as the concept of correlation. In this case, we're correlating damage with simplified damage, which operational damage, or with more, or with let's say preset a number of events. So all these capabilities are within this premium package. And when it comes to the look and feel, you can operate CAEfatigue in 3 different ways. In the middle, you see the control file. We have a control file, an input file that you can run, and then that's something that always can be done. But typically you don't want to create an ASCII file, right? By hand. So we have a GUI, interactive GUI, extremely powerful, a multi-tab. Essentially you can perform also parallel processing, run multiple jobs at the same time, and very, very versatile architecture. And last but not least, we can integrate the fatigue solver inside Nastran. We also have an integrated version inside Marc, and this is not used for customers. But let's say the big token here is being able to put inside Nastran the same fatigue process, and therefore when you run Nastran, you also get fatigue results as part of your Nastran analysis. And this is also in turn very valuable for robust design, because if you want to assess how the model changes affect the fatigue analysis, then you can do that with this unique all-included workflow. So from an interface point of view, I put a lot in this slide, so I'm just going to take it slowly. But as I said, we have this concept of templates. You open a template. In this case, it's a mature one, right? You open a template. This is an example of a time domain, and you start filling boxes. So in this case, we have multiple events, multiple channels that are superimposed. So this is a typical pseudo static or pseudo transient. It's more or less the same thing approach. And once you fill in the resources, which is your input results, typically in Nastran, there would be an H5 results or an OP2. Then you can browse our material database. You can put together by drag and drop a number of events, multiple CSV files or multiple RSP, whatever. And then you have to set up some parameters. When with these 3 steps, you press play and you get some results. Obviously, it could be more advanced. There could be specific needs around welds. You can then look at the beautiful post-processing capabilities that we have. If you are running, and then, as I said, process-oriented, preset template, drag and drop, help everywhere, multiple tab, which means to our detriment that you can open one single instance of CAEfatigue and control 5, 6, 20, or if it's in my case 200 different examples at the same time, and just with one click go to one to another. So this is to our detriment, because it's the same number of tokens instead of asking for repeat tokens every even if you have 5 or 6 models that you are visualizing at the same time. Maybe in the future we need to change this, because this is not giving us enough credits. But if you are working in the frequency domain, it's more of the same thing. So the frequency domain is not anymore a challenge. It's not anymore, let's say, a steep learning curve. It's really off from the start. You don't have to know too much, right? And it's good if you understand the concept of how linear dynamic system work. When you have a random response analysis, but we have input PSD instead of time domain loading. So power spectral density, in this case, is a simple example where you have X, Y, Z, so 3 different axes of vibration. And then you will have essentially 3 subcases in Nastran or whatever in ANSYS and so on. So X direction vibration with a certain exposure, Y direction with another exposure, and then you can check what direction is giving more damage. Okay, and this is just a very simple approach. We can do cross-correlated examples where you have simultaneously acting 3 channels or 200 channels. And last but not least, if you were into robust design, and again, this is coming along a bit with the request from David, how can we look at the effect of varying some of the parameters that led to an analysis? And again, this has got nothing to do, a lot to do with fatigue, right? Depending on how you want to see it. This could be a normal mode analysis. This could be a buckling nonlinear analysis. Eventually it could be vibroacoustic, like in this particular case, but it could easily be also fatigue analysis. And we get a distribution, a cloud of points, and that's how we could correlate with results, real life results that are scattered plot. And then we could even go a step beyond and try to adjust the model to meet a certain target. And this is more like my current response to what David was asking, but we can come back to this later. There will be a session dedicated to this. So at this stage, I just wanted to give you immediately an impact view of the scope. And this is not even like the full scope, but at least the fact that the unique beast that CAEfatigue is. And then I'm just going to go one step even farther to show you how many complementary tools that we have, all within the same philosophy, all within just a couple of clicks, and how they support this workflow, starting with real life problems that you want to address. So never really looking at fatigue. Oh, we do the SN curve, we calculate damage. No, we really look at the problem that you have, and how we can facilitate the process. So yeah, with this in mind, we have material databases that are embedded into the tool, but we can also accept any, let's say, more or less, we have multiple material models. We can accept nearly anything. And we have a very advanced workflow with Digimat, which means that essentially some tough materials, they cannot preemptively be described. Like, for example, with short fiber reinforced plastics, where the material really depends on the location because it's an injection molded part. And depending on where you look at the material, it has a different fiber density. And then depending on how you load it, it has a different loading direction or a different R ratio. So all these things means that the curve has to be detected on the fly. We can do that with Digimat. We're working more also on composite with Digimat for this capability as well. So that's the material angle. But on this other side here, that's an important, let's say, architectural fact in CAEfatigue that is unique: transparency. So yeah, you can work on the GUI as much as you want, but everything gets written in immediately parallel, inspectionable file. And everything is completely, you could work directly. We have capability for you to edit and work directly, intelligently on the input file. And if you are happy with the input file, this is immediately something that is, let's say, ready to run, right? You'll be running it, for example, on simulation data management or just on a server, not Linux server. Then you will be dropping your results back into, the fatigue folder and post-process. So again, very, very versatile architecture for multiple needs. The visual random response. I mean, this is really, as I mentioned, always been for many months and years, the tokens, the winning token for CAEfatigue, because we were the first really to let it all out like this. You have, in this case, for example, superposition of a power spectral density and a sine sweep, right? And then we perform, there is no fatigue analysis in this particular case, it's only random response. And you can see what happens here. Essentially, you have the input PSD, the transfer function, the resulting power spectral density, and then you can see how the frequency sweep is being picked up on the error mesh side. Okay, so yeah, it's so important to be able to visualize what you're doing, because this thing is riddled. Traditionally was riddled with traps, dimensional trap, coarseness in the transfer functions, auto sync, PSD input frequency with the way you sample the power spectral density, and the way we let it out makes it so easy. it's proven. And we, you know, it's random only, sign sweep only, combine random and sweep. We can do also displacement, vibration, and acceleration. So when it comes to random and, you know, even forces with monitor points, we can do collision detection, load cascading. So you have an assembly, you want to go from a big assembly to a tray, then you can look and dissect more specifically. And we also do this very efficiently from an American point of view. I put here hotspot detection, but in reality, we have a number of tools for filtering, which means essentially we can on the fly decide that we're only going to look at the smaller part of the model. And this might be a two-step process where you do a pre-filter and then a very, you know, coarse, let's say, frequency response analysis. Now you go, you know, in a very, very refined manner to get you know, a more correct answer. Okay, so with this, you know, some of the guys that are in the armored vehicle might be very familiar with this DEF standard. I bet you guys are. Some others might not look at this with particular pleasure, but you know, this is a you know, quite cumbersome requirement, a DEF standard that essentially has the power spectral density with narrowband. 3 narrowband that are moving up and down the frequency domain according to a kind of a sweep. You know, it's not a sine sweep, it's a narrowband sweep. And this is something that, you know, overnight, somebody asked me if we could do this. And I know overnight I created, you know, essentially using this out of the box, I created, you know, this template. And once it's there, you reuse it, you know, you change, it's all object oriented. I have the template, you know, you can, you know, see X direction, Y direction, Z direction, because this is happening on 3 axes. And now that this template is up there, you can change the battery, or you can change the electronic component and run it as many times as you want. And that's it. So out of the box. You can see, you know, the reason why this stuff is out of the box is because we worked a lot to put, you know, things that are needed in the box, thanks to, let's say, collaboration with a few key strategic partners in, you know, that worked with us on the development on CAEfatigue, and they are still working with us on the development of CAEfatigue. And you know, we really appreciate requirements, you know, the interaction with customers. And David essentially already given me inputs, and I look forward to, you know, these kind of challenges because the requirements really what feeds, you know, the success of this enterprise, right? So if I have very clear requirements, I can, you know, do my best to implement them. And you know, Colin said, you know, this very clear view of what was the challenge, what were the challenges, and they had a number of different tools in-house, sometimes not delivering the same results depending on who are using it. So they switched over to CAEfatigue for consistency, for speed, and ultimately, you know, to improve. To remove an in-house tool that was not so easy to maintain. So with that, I'm just going to step away from, let's say, traditional fatigue and talk about some of the complementary stuff that we have that are relevant, you know, super relevant actually, and also key to the success of the deployments of CAEfatigue in specific environments. Okay. I'm going to take a little bit of a breather if there is any question or request before I go into the next section. Okay, I'll move on then, and I'm going to talk about load management and what this means, essentially the preparation process that then feeds the data inside CAEfatigue. There's 2 angles to it, you know, time domain angle and frequency domain angle. And essentially, this is going to lead to, you know, a bigger, broader section that I'm not going to open today because it will be too, let's say, specific. But it's essentially test optimization, where we are working very hard. We'll be delivering more tools at the end of the year. So, you know, what we already have is absolutely quite fantastic. So when you see this roadmap, it might resonate with some of you guys, but typically when you have a vehicle, armored or not, or even an airplane landing, or just a photocopy machine, whatever your mining, let's say, excavator, or whatever is your assembly, you might, let's say, have assembly loads. You might acquire those loads experimentally, or you might use multi-body dynamics as a way to determine the loads. In this particular case, the component we're after could be maybe a chassis, is created as a flexible body. So we'll be roughly at about this point here, right? We have either acquired or we have calculated through Adams the loads. So every time you see a little red, let's say, symbol that represents a CAEfatigue, you can see that we have modules and capabilities that are targeting that particular, let's say, moment in time into the design process. For example, here, we don't have, at this point here, we don't even have a final element model. We just have acquired loads, right? We can already use CAEfatigue pseudo damage calculation to understand what events, what channels, what location, what directions are more likely to create problems, okay? And also, yeah, we can look obviously in the frequency domain, in the time domain. So it's already quite invaluable, instrument at this early stage. And you don't even have to have a final element model for that, or a multi-body dynamic model for that. Now, if you have the multi-body dynamic model, then you can already use that directly, calculate fatigue analysis on the model neutral file, for example, or you can pass the information, the loads information into Nastran or equivalent and perform time domain fatigue analysis, what we could call here body durability, okay? This could be done inside interactively, could be done with Nastran embedded fatigue, could be done with third party. Now, at this point, we might want to then decide to move into the frequency domain for a number of reasons. Because the load is random, because there is more efficiency, or because our ultimately desire is to really get to a laboratory test that represents a particular loading condition on a part or on a component of our assembly. It could be, I don't know, the battery tray. It could be a mirror. It could be an electronic component, right? And we need to get to test load that represents what's happening in the time domain. So this could be either for sign-off purposes, could be to just make sure that the part can sustain a level of vibration, or could be because you have provider. You could be either a supplier of an OEM, or you could be the OEM. They both have, let's say, a need, an intersection there. The OEM needs to provide to the supplier the loads, and the supplier needs to verify whether their parts sustain that level, for example, of vibration. So that's really sometimes the end game, okay? So to get to that end game, we go through a process. A process is, for example, first conditioning the loads, understanding what the loads have in them, in the frequency domain, filtering them, making sure that there is consistency here, quality in the data that we feed into the process downwards. And then we get to this, okay, we are in the frequency domain now. We have used our tool, this is called time to PSD, and we can perform random response analysis, much like I just showed you before, and we can do displacement, acceleration, velocity, forces, but also collision detection. What is the probability of two parts colliding? If you have a tightly packed component like a headlamp, for example, you want to make sure that there is no friction between parts. So this is just at the random response level. Now, if you want to go into body durability, but in the frequency domain, there is good reason for doing so, right? We can do this the easy way or the hard way, right? The hard way would be essentially looking at the one-to-one relationship with the multi-correlated loads that are acting in the time domain, and we can recreate exactly the same capability in the frequency domain. There's a number of reasons why you would want to do that. I'm not going to go into detail, but more than happy to do so if you are into this kind of game. Okay. Lastly, what I was saying is typically you won't want to look, well, typically quite often you want to go into a particular part of your design and look at what is that component status, right? You want to create a specific cascading on that particular component. And then ultimately, at this point, you are simulating the whole life, the whole operational life on that component, but ultimately maybe your target is to create a test in a laboratory that represent that whole life. So I think I need to stop at this point. Otherwise, I already told too much about this slide, but I just wanted to give you an idea, of the philosophy that is behind all the modules that I might referring to here and there, right? Is really trying to look at what you guys are doing on a day-to-day basis and how we can make it easier. So it's not about calculating fatigue. It's also about calculating fatigue, but it's that's only really portion of what we're trying to do here. Again, any question on this workflow before I move on to the next one? Either I'm super clear, which is okay, I take that, or you are overwhelmed or you're bored. Okay, so give me some sign at some point. I'm gonna carry on. Okay, so
No,
hopefully.
Well, I don't have any questions, so I'll raise my hand.
Okay. That's great, David. Thanks for
and I'm not sleeping yet either, so that's good.
It's also good. It's also good. It's early, but if you have already eaten, or maybe you need to go to eat, you probably want to rush this. Anyway, just for the record, yeah, when we look at this load conditioning, I oversimplified, talking about filtering, but what we're doing is really. I don't want to flatter our design team, but this is something that we are really proud of, right? Every time a customer looks into this, they realize that the alternative in MATLAB or in other, let's say, environment that are competing with us, it's absolutely, it's not a match. So we look at all these signals. You can see that they are not random. Stationary, they are random at time, because what happens here, maybe they're random, by the way, it's not even that clear, but you see that you are going around a proving ground, you're stopping, this is 3 different rides, or 4 different, let's say, loops, and maybe it's stopping and then starting, and you cannot convert this into the frequency domain right away. You need to filter out the events that are relevant. Maybe this first bit here is relative to a particular part, country road, and the next bit is relevant, is Belgian blocks. You cannot mix and match, right? You need to create sub-event, and we need to make sure that we create the power spectral density, let's say the equivalent, let's say environment in the frequency domain, the equivalent loading environment, in a way that is, as close as possible to the intention in the time domain. If we were to just filter out partially or just make one big lump of this, we'll probably end up with something that is not representative, because the information would be diluted. So what we do, we take a lot of things, automatically. You can interfere with it, but it's all automatically doing everything for you. You can literally loads of stuff, like in one click, drag and drop this event. And by the way, there could be like 5, 10, 20 events at the same time. You literally press play and it will do something which is going to be useful right from the start in a few seconds. Ultimately, we create the power spectral density, the direct ones, but also the cross correlations. And you could use this as an input matrix directly for random response analysis in Nastran, for example, because we use the same format, or inside CAEfatigue. So yeah, I think there is a video for this, just to give you an idea. You open a new process. Initially, there's nothing in here. Then you go here, file, input, and you just look at one RSP file. There could be, as I mentioned, 20 RSP files. In this case, it's very simple, 3 channels. Okay, we can filter this easily by saying, oh, I want to take from here to there because this other stuff is not useful, right? I'm going to say, okay, filter from here to there, and cut out that stuff. This is actually what I'm going to work on. But let's be more daring. Let's not do anything. Let's let the software decide automatically. So I'm going to take a window that purposely includes stuff that I don't want, right? And I'm going to use automatic detection capability in PSD, in time to PSD, to remove auto filter essentially, the signal, and based on some preset coarseness in the frequency domain, that means that can be shared across the company. I'm going to run this, and no matter if my colleague or myself or somebody else 6 months from now will run this, they will always get the same type of style PSD, which is very important, because it cannot be left to the interpretation of the, let's say, buffer, the windowing, and the FFT algorithm, right? We have a way to make this process very repeatable and very consistent. Ultimately, as I mentioned, we can look at this now and create envelopes and use the envelopes. If you want to do something very simplified, we can take this result as a random table that you can flash back inside Nastran, or you can use this thing directly inside CAEfatigue for more advanced cross correlation case. Okay, so that was an example. This is Stellantis, formerly Fiat Chrysler Automotive, using this. There is some papers that you can look at and understanding what is the value of all this. And yeah, I like to carry on the signal side and showing you how we can work on surrogates. Where I might get back to the surrogates at some point, because if this is relevant, but all the part. This is just the beginning, right? How we feed, the frequency domain process. But then there is a part, okay, we got to a result, but now what we want is create an equivalent, simplified loading condition that will create the same effect. But in a laboratory, for example, where I have a simple single axis vibration, right? We have a whole set of tools. They're doing exactly that, okay? If there is time and interest, I can cover some of that today, but otherwise, we'll have to, maybe, do this as a follow-on specifically for the people that are interested in those things. Now, I'm going to move into some other example of high-tight integration because some of you use other tools. Yeah, I mentioned about Nastran input fatigue. This is a simple Nastran embedded fatigue. This is a simple pictorial what it means to work interactively. So now you first run Nastran, and then you have very big models, multiple subcases, for example, and then you run, let's say, the fatigue tool on those results, right? So you literally get H5 and multiple H5 or multiple ODB from Abacus and multiple RST from ANSYS and so on. And then you can interactively create some fatigue results, okay? So there is two problems with that, but also advantages. Obviously, it's very nice, intuitive. You can do reporting, you can see what you're doing and so on. But, the fact that maybe this could be a very big job, right? And then you have to transfer the file across maybe a network. And there is a benefit in saying, okay, what if I include the fatigue process inside the Nastran job? Just basically you run the input file, you get the fatigue results, right? So there is not much more to say about it. And the additional value of doing just in one single go, so you can run on the server and get also the fatigue result, for example. But you can also leverage optimization tools that include also CAEfatigue, including robust design, okay? So not only optimization for fatigue, but also robust design workflows. Okay, so yeah, well, Nastran embedded fatigue, we supported. It used to be historically supported by Patran because Nastran embedded fatigue has been there even before CAEfatigue. But now, first of all, Nastran embedded fatigue now is completely based on the same engine. So when you run interactively, you get the same answers that you would get if you run Nastran embedded fatigue, because it's the same license, it's the same code, and we support essentially incrementing an initial Nastran input file. So you start with a PDF that is maybe a solution 101, and you can add fatigue, let's say, loads and fatigue cards and material cards through CAEfatigue. So essentially, CAEfatigue increments and export an Nastran input file that also includes the fatigue, let's say, card. So in initial solution 112, for example, will not have this fatigue card and will not have this FTG parameter or FSEC. They are defining essentially what's required for a fatigue analysis to run. And once you have, let's say, incremented your Nastran job, you can run it and you can read results all within the CAEfatigue interface. This is true for any NEF. It's not yet true for NEVF, which is, let's say, the equivalent in the frequency domain. Well, but we're working on that. In any case, it's partially supported right now. For Marc Mentet, which incidentally was exactly the previous presentation that I was having, like just an hour ago. So I'm fresh from reviewing the greatest and latest in this capability. So within Marc Mentet, that is our, let's say, premium nonlinear capability. We now have access directly to CAEfatigue library to solve for elastomer fatigue. And what this means is really completely different approach. It's based on crack energy density and essentially allows to perform a kind of linear elastic, sorry, not linear, a Paris law-like fatigue calculation to determine the more likely location where and the damage that can be accumulated. So to estimate the fatigue life of elastic elastomer component, and this is using a critical plane and linear elastic. Once again, cracking energy density and a Paris law-like tool to determine that. And it's extremely well integrated and very specific, obviously, for elastomers. This is something that we delivered only recently, but it's coming through very nicely. Some example of how, let's say, some customers taking advantage of running Nastran with integrated fatigue analysis. I mean, we're talking about models that are like, incredibly big, and getting fatigue results, getting any stress results on a car that is like 10 million elements is an absolute nightmare, right? Let alone then post-processing them for fatigue analysis. And CAEfatigue deliver integrated in Nastran delivers, let's say, the opportunity to avoid that cumbersome process of exporting this large number of results. With Romax, I'm just skipping to different workflow. If you're running Adams or if you're running Romax, you have direct connection with CAEfatigue. In the case of Romax, you can see this would be, for example, exporting a particular gear directly in a format that Nastran says in a Nastran OP2 result like that we can then leverage for fatigue analysis. In this case, you can maybe intuitively see that we have a different angle. We have a different, let's say, stress results, and then we essentially concatenate them into an engaging gear effect. And this obviously provides an extra gear, pun intended, to the Romax capability, because then we'll be providing full 3D, essentially, visualization of the tooth root, for example, criticality, so we can see exactly where the problem might occur. This is another example of integration. I did hint into this. When you have a very advanced, let's say, material requirement, such as in short fiber reinforced plastics, typically you have an initial injection molding analysis where essentially you fill this part with fibers and resin. And what you have ultimately is therefore a different, let's say, density and a different share of fiber direction depending on where you look in the part. And this information is available, right? It's stored. And CAEfatigue leverages on this information, and Digimat leverages on that information to create fatigue curves on the fly that are relevant for, element by element. There would be a different instance of the fatigue curve that we're going to be picking for calculating the fatigue life. Okay, this is fully integrated and available in CAEfatigue, both in the time and in the frequency domain. This is an example of a customer advanced, using this kind of materials for replacements, for metal replacements, and it's a nice presentation that was given in Italy. We can provide it to you if you're interested. So this is really looking at the whole workflow from Digimat, from injection molding, Digimat, so Apex, Marc, and then CAEfatigue for fatigue analysis. Okay, so again, I skipped on some subject, believe it or not, especially as I mentioned, the whole, let's say, generation surrogate loading, and did not mention the integration, for example, in vibroacoustic with Actron. So yeah, I did not dwell too much into the things that we can do for Adams, but at least hopefully you get a perspective of, let's say, the capabilities of CAEfatigue in the context of traditional, let's say, durability environment, okay, where it's testing optimization, fatigue analysis, load management, mission control synthesis, all these, surrogate loading, all these things are, let's say, something that we, I say we can deliver unique value proposition. Now, we can take robust design now as an extra leg, right? It might still blend into everything else, but it could also be seen as almost as a standalone capability on its own. So I'm going to just try to give you the gist. There is a very nice webinar I should have put into this slide. Well, once again, I flatter myself. It's just unashamedly, but I apologize for that. And I gave a webinar like 2 weeks ago, public one. You can watch it. It's dedicated to this. I'm just going to give you 2 or 3 slides, but you are more than welcome to. I can provide you the link. You're welcome to visit that webinar, and it will give you, 30, 35 minutes overview of the capability with some examples. So why would you want to do robust design? Well, nature is varying. It's you have uncertainties and you have variabilities. Okay, so uncertainties is, how can you know exactly what is the density of the material, what is the fatigue curve of the material? It's just a certain scatter, a certain uncertainty. You cannot nail with one single deterministic parameter a descriptor, right? You know that there is a certain bracket. But also some other things are just varying by nature, like the loading, how the customer is using your products. Okay, you cannot put a number on that. Sometimes people just say, okay, I'm gonna have a scaling factor to take into account. The load could be 10 to 20% more, right? But that's not really like a good way. Ideally, you would want to try to have an understanding of what is the, let's say, more likely behavior and what is the extreme behavior, and make an informed decision on exactly what the uncertainty effect is on your product. Okay, so this is the essentially robust design is the capability, is designing really taking into account that variability and uncertainty, incorporating it. Okay, so once we incorporate it, we carry it along, we incorporate it from the beginning. So part of your input is the uncertainty, right? And then you get a result that takes into account how uncertain your result is, right? It just gives you, quantifies it, right? So it's uncertainty quantification. You're doing this for realism, for credibility, for resilience, right? You want to reduce warranty. You want to expose yourself to, let's say, having to correct down the line unwanted behavior. But also you want to avoid over designing, right? You say, I'm going to put a factor of 10 here, factor of 12 there, and so on and so forth. And by the end of it, you have a very robust structure, but maybe too robust, right? And it's not necessary. So with this brief introduction to the problems, you might spot, let's say, the devil immediately. Say, okay, but I don't know the variability, right? Well, how do you define variability in my components? So first of all, the very, let's say, the non-dimensional standard to define variability is the coefficient of variation, which is the standard deviation divided by the mean value. And with this, obviously, this means that you get a set number that is irrespective of the value of the quantity, and the variability can be in material properties, in geometry, description, tolerances, manufacturing processes, you name it, everywhere, right? But the point is, even though some industry, like for example in aerospace and defense, they have very tight margins. So in space, for example, and they try to investigate what is the effect of variability to certain characteristics, right? And you can see here, if you scroll a bit the numbers, it's never really above below 5%, right? Never. It's sometimes it's dramatically high. But what I'm trying to say here is that if you just make a initial conservative assumption that you can always go back and correct, that you have a 5% flat uncertainty everywhere, you're not far from the truth. Okay, and this means that quantifying this variability is useful, but it's not necessary to take benefit and to start enhancing your design with the robustness investigation. So What happens in CAEfatigue? You have a template, okay? Template, it's, once again, you open it, you don't have, in this particular case, you have to learn nearly anything at all. You just have to have a running Nastran model. Could be solution 101, could be solution 112, it could be an F integrated job that does, I don't know, a static and fatigue or vibration and fatigue. And what we do in one click, we look at the model as a model tree, and we essentially allow you a randomization with a couple of click. You right click and say randomize all these properties. Then what happens? You run a DOE, which is based on Latin hypercube sampling, which means that 100 runs cover a significant part of the investigation, and then you get statistics showing, for example, in this case, normal modes. The first normal modes goes from 30.7 hertz all the way to 34.3 hertz with an average value of 32.6. So the nominal value initially would have been 32.6, but then you can see that even for the first normal modes, you might have a 2 hertz bracket up and down. And this is quite important initial piece of information. And this can be captured with clouds, pipe charts, understand, showing at the different level of relevance for different parameters on the end results. And also, more importantly, this decision map is the key to understanding the relationship between parameters. What parameters affect what output results? And the size of these blue dots here are indicating exactly that. If there is a relationship between input, the yellow boxes, and the output, the blue boxes, then you will be immediately seeing what it is. So yeah, again, I could literally go on for hours on this, but just showing you. If you look at that webinar, you will see the latest and greatest, even newer capability that I haven't not included in these couple of slides. You can see here, for example, a vibroacoustic case, and we can track, in terms of envelope, all the frequency response of a particular, for example, accelerometer or pressure, sound pressure, as it varies in frequency. So then we can go at a particular frequency range, let's say between 50 and 60 and 70, 50 and 60 hertz, where there is, let's say, starting to be audible, and we might decide, if this was a comfort, like in space, there is no such need. But let's say we might decide to dwell down into that particular range and try to understand how can we reduce this peak, right? Or maybe we do it more realistically. In this case, we do a fatigue analysis. We realize that this particular peak is very influential to the, because it's going to be a wide band loading. This might be very influential to the end RMS and the moment of the power spectral density, and it will be affecting negatively the vibration results, and especially the fatigue results. And we might want to find a way to reduce this peak. So we can use robust design to go back to this, and even, to be honest, even adapt robust design. So we have a way to convert this problem into a recursive iterative problem that does adjustments to certain design parameters to meet a certain target. And this, David, this is what I was trying to get at the beginning, that we do have some capability already, but we're working to deliver even more correlation tools that are specifically, let's say, intended to work with provided data. For example, looking at model assurance criteria and things that can support correlation with test results. But here you could feed a certain target value and find automatically a way to change your model, certain selected parameters that would deliver that results. For example, again, I'm dwelling a lot here. I'm asking a lot of imagination here. But if this is the response, right, at a certain frequency, we know that damping is a function of frequency. Okay, so it's not easy. Right from the start, you typically define a certain damping function that is flat all across the frequency. But then in real life, it's hard to match. Maybe you get this peak right, but not this other peak, right? And this could be due because there is a frequency damping effect that is needs to be tackled. And you could use robust design to change automatically to adjust that damping to meet a certain target. hopefully with this, quick overview, I need to stop to give you time to ask questions. There's a few examples of how robust design has really been helped in a couple of, in 3 or 4 industrial cases that we can at least show. And then I think the conclusion is that we focused on streamline processes. We focused on helping expert, but also non-expert. And we focused on performances. Okay. So yeah, I think hopefully I delivered that, and maybe we can still have 3 or 4 minutes or 5 minutes. I'm here actually. I can stay a bit longer, but if you have some questions or comments.
My first comment won't go to you. It'll go to Gerrit, and it'll sound like this. How much does it cost? And I assume it's included in my current license.
The moment you go to MSC1, it's in your license, yes.
It should be in my current other one as well. Nice try. Polly's outside. Yeah, I could get a 2-year trial license.
Funny.
Why not 5? I mean, if you give us something back, we may consider that. But
no, I know. Look, don't defend Gerrit and Paul. They are very good. They do work closely with us. I just like giving them a hard time. It is a very powerful tool, and I think there's good applications for it here. Thank you.
That's great. Thanks for the kind feedback. I forgot to mention that obviously this is part of the token system. You could, you remember the packaging. There was time, random, frequency, and premium, right? They obviously suck, increasingly more tokens. Like well, actually, time and random, in robust design, they only need 15 tokens right now. I'm gonna start complaining because I think it's too little. So hurry up, make your purchase because we have to bump it. But the frequency version, the one that does vibration fatigue analysis, requires 25 tokens. And the whole comprehensive, so when you want to do surrogate loading, when you want to do combined deterministic and frequency domain loading, that is 48 tokens. Okay, so that is the only one that uses a good reasonable pool of tokens. Otherwise, every other, let's say, fatigue capability is well within, let's say, the very confined 25 tokens is a reasonable small pool that allows you to do a lot. Okay, and this means that you could run Nastran and then close Nastran and run CAEfatigue. You could run Marc and close Marc and then run CAEfatigue. You could do, and then you can do also Digimat, all these other things. Let's say as if you want to combine and do Digimat and premium medicine and premium fatigue and so on. So that's when obviously the token count needs to be a bit more consistent. But this is also reflecting quite advanced value and capabilities. And obviously, all of these are also purchasable as a standalone. You don't have to have token system. You could also purchase them as standalone module. Thanks.
As I said, Paul is actually, we're about to talk about our software as soon as we finished. Yeah, that's why I'm smiling. Let's see if he says exactly what you told me now.
Okay, very good, very good. We're aligned. So yeah, I just wanted to, there's a bit here, an overview of some of the, the progress that we've made.
I'm sorry, while you're busy doing with this, I forgot, and I must admit, I apologize, I joined a few minutes late. The presentation is available. Gerrit will send us the link where we can find it on the site.
Yeah, I might put the link even on this chat, but
okay.
So I can share the presentation, of course, that I gave. And but also the link to that robust design capability. Couple of things just to give you an idea of the things that we're working on. We are continuously improving that power time to PSD capability with new algorithm that do things improving what's already very good. The pseudo damage stuff, it's really good, guys. I mean, we're not doing a good job of showing this off, right? But you look at multiple, this is no fun element whatsoever, just data, right? And then you look at our different channels in different events. This could be the same strain gauge under different conditions. and it could be different directions, it could be different location. Immediately you get a sense of where the problem could be, and then you can rainflow, cycle count, even look at particular peak in time, and we can do this in the time, in the frequency domain, and then we can decide, okay, if I want to have, this is just like, say, when you do a power spectral density, when you do a pseudo damage, you essentially look for a damage one, based on that channel. That's why it's called pseudo. Even if it's acceleration, even if it's force, you can still get a damage number. Okay, you're just going to pretend that it's stress. But when you do this in the time domain, in the frequency domain, you get a different scaling factor to that damage one, and then we can use an algorithm to do adjustment. And this means essentially we get an adjustment factor so that the frequency domain equivalent will produce a damage that is similar to the time domain. And then you can use this as to work in the frequency domain. That's just one of the way we operate. We can look at the kurtosis because sometimes some of these loads are not really random, as random as we would like them to be, like Gaussian, random, and stationary. And you can check the pattern, and sometimes the kurtosis reflects also the adjustment factors. And you can see that the more kurtosic, the more, let's say, rebalancing on the adjustments, which is very cool features. And yeah, it gets more complicated, right? I don't want to overcomplicate stuff, but the idea is that you get a very complicated set of loads in real life. You want to go into a Schicke table with a single power spectral density that represents as best as possible that complexity. I mean, you need to find a compromise, right? And we help you doing that. And what's beyond? We're gonna make more improvements. We're gonna introduce with fatigue damage response. Fatigue damage spectrum as part of that of this surrogate loading. We already have 3 or 4 tools, but we're gonna add also this other one because people are familiar with fatigue damage spectrum. We're gonna look into shock response spectrum in the next release. We're creating an API for you guys to be able to run your own methods if you want to. And we're looking to composite fatigue, with Digimat, so much like you saw for short fiber reinforced plastic. But we're going to do it also for continuous fiber. So, we are, very excited about the progress and what we are delivering. Okay, so I stopped the marketing pitch. You can, I'm always within a couple of clicks away, and the guys at SIMTEQ know that, and they. I wouldn't say abuse this at all because they don't call me enough, maybe, but they do call me, and I'm always going to be available for any specific follow-up. And as I said, if you have requirements that you think we should be considering, I'm the requirements guy. Okay, so let me know if you need any help with anything. I'll share the information. I'll put in the chat. The chat will stay live. The link to that external webinar, you can start looking at that. And I'll share the presentation with the colleagues in South Africa so that they can provide it to you in PDF. Okay. Garrett, any final comment? I think we overran a bit. I don't mind, but I don't want to be impolite.
No, thanks, Marco. That was really excellent. I always look forward to a presentation from you, but even more so from the new features. There's a couple of things I'm looking forward to play around with and test out and so on. So thank you very much for the presentation, Marco.
Keep asking questions to Garrett so he learns more about CAEfatigue, and so I don't have to answer the questions for him. But yeah, Garrett always has familiarity already, so that's why it doesn't bother me too much. Let's put it this way, because he already has the answers, in many cases. Okay, so we look forward to collaborating even more with the new feature, Garrett.
Okay, thanks again, Marco.
Thanks everybody. Thanks for
thank you very much
this afternoon, and have a good weekend. Bye.
Bye.